Right. I think you guys can properly hear me. So there might be some sort of interruptions because of the signal issues. So here we are facing some sort of rainy situation here. So if you are having any trouble, please do use the chat box, right? And if I'm like, you can interact with me by using the chat box and yeah, right. Okay. So last week before the New Year's vacation. In the last session, we started this magnetism section and we discussed several parts up to the magnetic field lines and how to analyze those magnetic field lines practically, the experiments that we can conduct. And also, as I can remember, we discussed about induced magnetism as well. So today, from today onwards, we need to discuss about the electromagnetism, which is an important part in this course unit, and hopefully we can start the motor effects and yeah, electromagnetic induction as well. Right. So just give me a minute. I need to share my screen with you guys. Then we can start it. Okay. So just give me a few minutes. Then I can start it. Right. So here, electromagnetism, yeah. So electromagnetism is the phenomenon, right? Electromagnetism is the phenomenon where there's going to be a generated magnetic field because of a flowing electricity, right? So here, when there's a current in a wire or any sort of what you call that conducting material, right? Current in a wire. So that is the most crucial part. You need to have some sort of a current going through the wire, right? It is like it won't be just a wire, right? If you are having just a wire, there won't be a magnetic field generated. So definitely remember. So just imagine in this case, I am applying a switch here, right? I am applying a switch and I'm going to keep it in the open configuration. The switch is open, so which means that the circuit is not completed, right? It is not completed. So therefore, what will happen is, so there won't be a current flowing through this system. So therefore, there's no current. So we cannot observe this sort of a magnetic field, right? We cannot observe this sort of a magnetic field. But if you switch this thing on, right? Now you are having a current. So current means like you are having that electron movement, right? There's an electron movement. So because of that, what will happen? There will be a generated magnetic field. So that phenomenon or that process is known as electromagnetism. So as the term refers, electromagnetism. It is not just the magnetism, electromagnetism, right? Which means, which gives the idea that the magnetism, a magnetic power is being generated because of the current, right? Or a flowing current. Okay. So write down the topic electromagnetism, or you can use the workbook I have given you, right? So electromagnetism is the phenomenon where you can write your own note if you wish, right? Electromagnetism is the phenomenon where a magnetic field is generated, where a magnetic field is generated is the phenomenon where a magnetic field is generated because of flowing current, because of flowing current. So underline the term flowing current. Remember that thing. It is just not the current, right? Not just a wire. You need to have a flowing current. You need to have a flowing current through that conducting material. Okay. So here a simple practical setup is being given here. So you can see that. So when this circuit is completed, right? So here we have placed the wire going through the paper. right? And there's a plotting compass as well. And also we have applied the iron fillings onto the paper, right? So once the switch is on and once the circuit is completed, what will happen is that these iron fillings will be arranged in a manner like this. So we are familiar with this type of arrangement, right? So this arrangement gives us the magnetic field lines, and by using the plotting compasses, right, we can determine the direction of the magnetic field. So here in this case, we can say that the magnetic field is in this direction, right? The magnetic field is in this direction, acting on this direction, right? So, um, right, no need of writing this stuff. Uh, just wait, I need to use another screen to explain these things, right? So just give me a minute. Okay, just yeah, wait a second. Right. I think you can clearly see the board here, right? Okay. So as I was telling you guys, so here the current direction is in this direction. So this is the current direction. And according to this experiment, you can see that the magnetic field is generated like this. The magnetic field generated like this, right? So in order to get this, so current, and this is the magnetic field, that is the magnetic field. So in order to get this, the direction of the current or the magnetic field direction, we are using a special rule that is called the right hand swirl rule, right? That is the right hand swirl rule. So the rule, it says something like this, right? So you are using the right hand. Okay, I'm going to draw one. So, and so this thumb, right? So this thumb gives us the direction of the current, right? So the thumb is the direction of the current. Thumb is the direction of the current. And the other four fingers, right? So now you are going to bend those fingers like this, right? And you are going to keep your hand like this. So the other fingers bent in this direction, making a curved direction like this, right? So that gives us the direction of the generated magnetic field, right? So this is the most important thing, right? So in this unit, we are using two different rules. So the number one, the first rule that you are coming across is going to be the right hand swirl rule. So this is just a simple one, right? So you can place your hand, you can place your fingers like this, right? And try yourself, right? So The reason is like in the exam, you need to use these rules in order to determine the direction of the current or the generated, the direction of the generated or the formed magnetic field direction. Okay. So remember this point. I think in the workbook it's given there. So no need of drawing, but remember how to use it. Okay. So which means if you are having a current in this direction, according to this diagram, in the upper direction, so there will be a magnetic field generated in the direction as given here, right? So just imagine if the current is going in this direction, right? If the current is going downwards like this, then place your fingers like that, right? And see what will happen. So thumb gives us the direction of the current, which means all the other four fingers will be bent in the other way around. So which means the magnetic field will be generated like this, right? So this is the magnetic field direction, right? That is the magnetic field direction. So please pay attention to those things and you need to judge the direction by your own, right? So if you are having any trouble related to this, you can use the chat box before I am moving on to the next section, right? So just give me a thumbs up, then I can understand whether you understood or not. Okay. Yes. Okay, great. Right. We'll discuss about the next one. So here, the magnetic field's strength, right? So this magnetic field strength, it depends on several factors actually, right? It depends on several factors. So here we are dealing with the strength of the magnetic field, right? Strength of the magnetic field. So the first one is if we increase the current, which is flowing in the wire, then you will be getting a higher magnetic field. The strength will be higher, right? Increasing the current will result strength increases. I'll write it like that, right? Magnetic field strength increases. Okay. Then another thing is that the second factor is that if we like just imagine instead of using a single line of a wire, right? If somehow if we manage to just imagine like prepare or like let's say we manage to arrange this wire as a coil, right? So instead of a single wire like this, instead of that, I am arranging it like a coil, right? So this sort of a structure, this is known as a solenoid, right? This is known as a solenoid. So if we apply, if we make the wire as a solenoid version, right? Then also the magnetic field strength will be increased. The magnetic field strength increases, right? Magnetic field strength increases. So remember these 2 points. Either you need to increase the current or in the other way around, you need to arrange the wire as a into a coil or into a solenoid, right? Both are correct. You can arrange it as a coil as well, right? As a coil as well. And also The third point, we can increase the number of turns in the coil, right? So remember the factors. First one, we can increase the current in the solenoid or we can increase the current in the wire. Second one, the wire can be arranged as a coil, and while making it as a coil, we can increase the number of turns there, right? Number of turns. So for example, let's say I'm arranging the same wire in this sort of a manner. And in the second situation, let's say I am arranging the wire having more number of turns, right? Having higher number of turns like this, right? So if we take this one to be A, this is to be B, then when it comes to magnetic field strength, the magnetic field strength, B is having a higher strength than A. The reason is in the structure B, you can see there are more number of coils, number of turns than structure A, right? Okay, so here you can write down these points. I'll give you a few more minutes. Once after you have finished, just give me a thumbs up, then we can move on to the next section. I think most of the points are given in the workbook. So if you don't have the workbook with you, then it's okay to write down these notes in just a paper, and afterwards you can uh, complete the workbook. And remember, most probably like by next week, we will be able to finish these theory parts related to magnetism. And once after all the theory are discussed, then we will be starting discussion of the past paper questions, right? So it's better to have that past paper question booklet as a hard copy, right? Try to print it and get it as a hard copy. Okay, time is now. Then in your textbook, extension work is given there. So the process of the working mechanism, actually, working mechanism of the electric bell and the circuit breakers are given there. So my advice is, though it is given under the extension work, it's better to go through it, right? So here I'll write uh, extra work. You need to know how this electromagnetism is used in day-to-day operations, actually, right? So here, the first one is the electric bell, and the second one is the circuit breaker. So the circuit breaker and the fuse are two different ones, right? Are two different things. So circuit breaker and the fuses are two different ones. The reason is like in a fuse, you have a metal wire. So once the fuse is burned, then you need to replace it, right? But in a circuit breaker, what will happen when the switch goes off, then you can put that put that switch on, switch back on, right? So that is the main difference. Remember how the working mechanism, what are the working mechanisms of these two equipments, right? Then, so that is the end for the first section under magnetism. So under this section, we discussed about magnetic field lines mainly. Like in the exam, you will be asked to draw those magnetic field lines. Likewise, there will be some simple questions, right? And last week, I can't remember the last session also, we discussed how to determine the wrong magnetic fields. Likewise, I gave you so many extra hint points, right? Okay, then the second section of this magnetism unit is about the electric motors and the electromagnetic induction, right? Electromagnetic induction. So induction term, I think last week also I explained what is meant by induction. Induction means generation of some sort of a property because of an external influence, right? Because of an external influence, right? So here we'll discuss about this thing. So in order to discuss it, I am going to shift to another shared screen. So just give me a second. Right. So I think you can see the shared screen. Okay. So here, uh, when it comes to this electromagnetic induction, the overlapping of magnetic fields is so much important, right? Overlapping of magnetic field lines or overlapping of magnetic fields. So overlapping means it is going above another one, right? That is the simplest idea of overlapping, right? So here, in order to explain this situation, this scenario, I'm going to use two different setups, but I'm going to combine it. So I'm having this sort of a magnet, right? This sort of a magnet. So here you can see in this section, you are having an uniform magnetic field, right? So in this section, these blue colored arrows, they represent an uniform magnetic field pointing from north to south, right? Pointing from north to south. And in the meantime, so this is going to be my second setup, right? So I have implemented an electric circuit here. So the first one is the magnet, which is having a shape and generating an uniform magnetic field. And the second setup is this working electric circuit, right? So here you can see there's a switch as well, but in this situation, the switch is in the on state, right? So which means in this direction, right? In this direction, the current flows. And here also, in this direction, the current flows. And here you can see current is flowing through the magnetic field. So this magnetic field is already made one, right? It is an already made one. It is generated by this permanent magnet here. But here you can see there's a wire being placed on the magnetic field, right? There's a wire being placed on the magnetic field. And the most important thing is that there's a current going through the wire, right? There's a current going through the wire. So what will happen is that, so in the previous case we discussed, if there's a wire which is having uh, having let's say if there's a wire which has a flowing current, so there will be a magnetic field generated, right? There will be a magnetic field generated. So now put on the chat box, use the chat and tell me what will be the direction of this magnetic field which is going to be generated because of the wire, right? I'll give you two answers here. Just tell me whether it is A or B, right? So if we consider this is the cross section of the wire, right? My answer A, it is going to be, let's say, the magnetic field is being generated in this direction. So this is the answer A. And the next answer, I'll say the magnetic field is in this direction. So this is answer B. Now tell me, use the right hand swirl rule, right? Right hand swirl rule and tell me what is the direction of the generated magnetic field in the wire. Yes, use the chat box. Yeah, good. Correct. That is the direction of A, right? Which means here the magnetic field, there's a generated magnetic field around the wire like this, right? There's a magnetic field generated around the wire like this. So that situation is given here in separate manner, right? So this magnetic field is due to the permanent magnet. Okay. This is due to the permanent magnet. And in the meantime, there's a wire being placed. So therefore, there's a magnetic field like this in this direction. So the actual thing is, right? The actual thing is this wire is also placed in here, right? It is also placed in there. So therefore, here you are having the wire like this. And in the meantime, what will happen, since there's a current flowing through it, you are having a magnetic field generated around the wire like this. Okay. So now pay attention to the direction of the arrows, right? So here you can see in the lower part, the resultant magnetic field lines, right? The resultant magnetic field. So the permanent magnet, the magnetic power from the permanent magnet and the generated magnetic power from the wire both lies in the same direction, right? Both lies in the same direction, which means here you will be having so many magnetic field lines. But in this case, what will happen is that the directions are in opposite directions, right? So which means they will be minimized, right? They will be minimized. So the resultant magnetic field is something like this. Now pay attention to it. Okay. Now see what has happened. So here you can see that at the bottom part, here you are having a strong magnetic field, and in the upper part, so the magnetic power is being reduced, right? The magnetic power is being reduced. The reason is these two directions are in opposite directions. So therefore, what will happen? So in this section, you are experiencing a low power or a low force, and here you are experiencing a higher power. So therefore, there's a power difference actually, right? There's a force difference. Sorry, there's a force difference. The force difference is from the lower section to the upper section. So therefore, what will happen? The wire will be like it will be pushed toward the upper section. So that situation, that moment, that is known as the motor effect, right? That is known as the motor effect or electromagnetic induction, right? We can say it like that. Okay. So just tell me whether you got the theory part here. Just give me a thumbs up, then I
Sir, can
can
you explain
move
that
on to the
part
next one.
again?
Sorry, Lamido, I can't hear
Sir, can
because
you
I am
explain that
using
part again?
just an external mic. So you need to use the chat box. I don't have any sort of speaker or something like that. If you are having any sort of trouble, just use the chat. I don't have my headphones with me today. That's the issue. I'm using an external mic, so there's only one way. Okay, so right, I'll use another shared screen, then I will explain it. Okay, just give me a minute. Right, right. So I'm going to draw the whole setup here. Mm, I'm going to draw it bigger, then you can clearly understand it. Okay. So just imagine this is the permanent magnet that I'm going to use. And this is the North Pole and this is the South Pole. So which means in this direction, you are having the magnetic field which is generated by the permanent magnet, right? You got that point? Ne? Okay. Then I'm going to place a wire like this. So this is the cross-section area of the wire, right? We are looking from the forward or from the in front of the wire, right? Actually, the wire is going through the magnetic field. And also another thing I wanted to explain here, I forgot it. So in normally like if just imagine you need to say like let's say something is coming out of the plane, right? So if we consider this flat surface, this screen to be the flat plane, right? And just imagine something is coming towards you, then we are using a symbol like this, right? We are using a symbol like this, which means this parameter, or let's say this any parameter, right? It is this is coming towards you. This is coming towards you. And if you are using a symbol like this across, so it means it is going away from you, right? It is going away from you towards the plane, right? It is going away from you towards the plane. So in this case, so I'll use this symbol as well. So the current is, if you consider about the previous diagram, the current is coming towards you, right? So therefore, I'll mark the current like this. So the current is coming towards you. Then once after you apply the right hand swirl rule, so I'll use the white color. The magnetic field generated because of the wire, it will be in this direction, like this, right? So the direction like this. And there I'll draw some other lines as well. So the direction is like this, right? So I want you to consider about this section and this section here, right? So at the lower part, you can see that both lines are having the same direction of the arrows, right? Which means in this section, you will experience higher magnetism, right? A higher magnetic power, a higher magnetic force. But in the other one, you can see that some arrows are going like this and the other ones are going in this direction. So arrows are in opposite directions. So therefore, here you will be experiencing a low magnetism. Why? The reason is the arrows are pointing in opposite directions, right? The wires are pointing in opposite directions. So this is something like the resultant force thing, right? So just imagine something like that. So if you are having, so in the first unit, we discussed about these things. If two forces, let's say F1 and F2 are in these two directions, in the same direction, so the resultant will be F1 plus F2. And if F1 in this direction and if F2 is in this direction, so the resultant will be F1 minus F2, or you can write F2 minus F1. So that is the gap between those two. So if we consider the values here, definitely this R1 and R2, so definitely R2 value will be lower than R1. The reason is you are considering about the gap here, right? You are considering about the gap. You are not taking the summation here as in the previous case. So the same thing implies here also, right? We are dealing with the forces here, right? Magnetic forces. So in that case, you can see here you are having a low magnetic power and here it is high magnetic power. The reason is here the magnetic field lines lies on the same direction and this thing having opposite directions. So therefore, there's a force difference. So the force difference, right? As in chemistry as well, like in that diffusion thing as well, right? So the higher part will be pointing towards the lower part. So here you are having a high power or high force, and here you are having a low force. So therefore, from higher force to lower force, there will be a force pointing, right? There will be a force pointing upwards. So therefore, that force will be acting on the wire. So therefore, the wire will be lifted upwards. Just imagine in the next situation. So I'm going to give something like this. So here we have the magnetic field lying like this. I'm not going to draw the whole setup. I'm going to just draw this one. Right. So now the magnetic field, the uniform magnetic field like this. And in this case, also I'm going to place the wire. Okay. But now I'm going to change the direction of the current. So instead of in the previous case, the current is coming towards you, right? It is coming towards you away from the plane. And in this case, I'm going to change the current direction. So now current direction goes towards the plane. Okay. Now the current direction goes towards the plane. It is going inwards, right? Now tell me what will be the direction of the generated magnetic field. I'm asking whether it is going to be clockwise direction or anti-clockwise direction. So this is clockwise. I will say A, and this is anti-clockwise. This is B. Yes. Tell me the generated magnetic field. The generated magnetic field direction. Is it going to be A or B around the wire? Just use the swirl rule. That's all. Yes. Is it going to be A or B? Yes, good. It is going to be, wait, it is going to be A, right? It is going to be A, right? Now you are going to place the thumb towards the plane, right? Not coming away from the plane. Okay. So therefore, now the generated magnetic field will be getting the direction of A in clockwise direction. So now you will be having a generated magnetic field around the wire like this. Now pay attention to the arrowheads. So here you can see the generated direction and the uniform direction. So both are lies in the same direction. So which means in this section, you will be experiencing a higher magnetic field, magnetic force, right? So here you will be having a higher magnetic force. And in the other way around, so here you can see they are in two different directions, right? They are in two different directions. One here and the other one going in this direction. So therefore, here you will be having a low magnetic force. So now the higher and the lower forces are being changed, right? They are being shifted. So therefore, what will happen? Now there will be a force applied downwards like this. So there will be a force applied downwards on the wire, which means the wire eventually it will move downwards. So, but in the previous case, what happened? It will go up. But now it goes down like this. Okay. So tell me whether you got did you understand the theory part? Just give me a thumbs up, then I can understand, right? Okay, good. Okay, right. So it's better if we draw this setup. Not my one. If you need, you can draw that one, but it's better if you can refer the page number 207, right? Page 207, it's given there. So I want you to draw those A, B, and the final resultant one, right? The final resultant one. And also, uh, the explanation is given there that, yeah, under those diagrams, the explanations are given. So better to write it. Okay. So I'll give you a few more minutes. Once after finish, just give me a thumbs up. Then we can move on to the next one. So remember what happens with these external magnetic fields. Okay. Right. Or shall I move on? So if you got it if you understand this, then there's no point of like wasting time here. So you can complete it for homework, right? We'll move on to the next theory part. Since we are running out of time, then we can discuss it. So if you're having any trouble, just drop me a WhatsApp message. Then, yeah, drop me a WhatsApp message. Then we can discuss about it. Okay. So without using these sort of diagrams, just imagine. So in all the cases, all the situations, we need to draw the magnetic field lines and we need to deduce the direction. Like those are some complicated things, right? So, and even like time consuming things. So therefore, there's a what do you call that? Yeah, I think it is, I can't remember the exact name of the scientist. So, the scientist, the final name, the surname was Flemings. So, he introduced a law, right? He introduced a law. So, by using that law, easily, we can easily get the direction of these movements and all the stuff, right? So, I'll explain it. So, yeah. Remember, when it comes to Fleming's laws, uh, there are two laws, right? Right hand rule and the left hand rule. So in your level, only on this O-level physics, right? IGCSE physics, we only discuss about the left hand rule. There's no need of knowing the right hand rule, right? So I'm going to emphasize that. But if you are studying A-level physics, then you need to know the other laws as well, right? So I'm going to write the topic here, that is the Fleming's left-hand rule, right? Fleming's left-hand rule, okay? It is the left hand, right? Remember that. So in the previous case, what we had, that is the right hand swirl rule, right? So most of the students, they just they get confused with these two laws, right? And eventually lose marks. So here, remember, there are two laws, Fleming's left-hand rule and the right-hand swirl rule. So first we discussed about the right-hand swirl rule. So I'm not going to draw the hand. Instead of, I'm going to use the theory part here. So if the current is like this, then the generated magnetic field will be in this direction. So normally in physics, right, in A-level physics, in order to display or in order to denote the magnetic field, we are using capital B, right? The symbol is capital B. So I'll write it there. The magnetic field will be denoted by capital B, not beta, capital B. So therefore, the generated one will be like this. So this is the left hand swirl rule. Okay. Sorry, right hand swirl rule. Okay. So that is the thing that you need to remember. And now, when it comes to the Fleming's left hand rule, uh, I have to draw a left hand. So now listen properly. Your thumb will be placed like this. And the next finger will be placed like this. And the middle finger will be placed like this. Forgive me for my bad drawing. Okay. So these are three fingers, right? Index finger and the middle finger, right? And there are two fingers left. Ne? So those two will be bent like this. Yeah, five fingers. And then the rest of the hand like this. Okay. So forgive me for my bad drawing, right? So these are the fingers. And the main thing is that between these first three fingers, the angle must be 90 degrees, right? So I'm not going to draw that thing. You need to remember it, okay? Remember the angles between these three fingers are 90 degrees, right? 90 degrees. And so here, from the thumb, we can get the force, the direction of the force. It will be pointing like that. And from the index finger, this is the direction of the current. Oh no, sorry. That is the direction of the magnetic field. I'll use a different color. So this is the direction of the magnetic field. Okay, this is the direction of the magnetic field. And the middle finger, it will be pointing towards the direction of the current. The current direction. Okay. So which means you can easily remember something like this, right? I think you all are familiar with the term FBI. So FBI is for the Federal Bureau of Investigation. But in this case, that lettering order will be like, helping us to remember this. It will be helping us to remember the order actually, the fingers order, right? So here I'm going to grab F from here. So thumb will give you the direction of the force. Index finger, it will give you the direction of the magnetic field. And middle finger, it will be giving you the direction of the current, right? I think by using that term, that lettering term, FBI, you can get the idea, right? And here the magnetic field. So magnetic field direction pointing like that. So which means from north to south, right? It is from north to south. And current direction likewise, right? From the positive end to the negative end. So if I draw the simplified version of the Fleming's left-hand rule, then it will be something like this, right? So here, this is force. This is the direction of magnetic field, 90 degrees angle. And here, this is the direction of current. So here also 90 degrees. And these two also 90 degrees. So this is the simplified diagram for the Fleming's left-hand rule. Okay, like this. So now don't just mix with these two together, right? So the right-hand swirl rule, we are dealing with just the current and the magnetic field. But when it comes to the Fleming's left-hand rule, we are dealing with the force as well, right? So just imagine in a question, if they are asking the movement direction, right? If they are asking the movement direction, so I'll write it here, right? In the question, if they ask about the movement of an object, so definitely then you are going for the Fleming's left-hand rule. If they ask about just the magnetic field and the current, then you are going for the right-hand rule, right? Right-hand swirl rule. Okay. And when you are using this left-hand rule, it's better to write that point as well by using the Fleming's left-hand rule. Then you can judge the values. And the important points here, special points. So when we are considering about the current direction, right? Current direction. So it will be from the positive terminal towards the negative terminal, right? Positive terminal to the negative terminal. Positive terminal to the negative terminal. Right. And there's a special case if there's a negative species, right? If there's a negative species, which means it can be either electrons or any sort of a negative ion, right? So this thing is for the positive ions, definitely for the positive ions. And if you are dealing with negative ions, for example, electrons or the negative, any sort of negative ions, then we know that, right? If the current direction is in this way, the movement of electrons will be in the opposite direction, right? We know about it. Okay. So which means you need to consider this point. The direction of the current is opposite to the movement direction of electrons, right? The direction of the current is opposite to the movement direction of the electrons. The reason is like this thing is not tested actually, right? And even it is not given in your textbook as well. But I got like we came across just like I can't remember just a small question where you are having electrons in that, right? So in that case, the direction of the current must be changed. For example, there are so many questions related something like this. Okay, so this is the like a common pattern of questions, right? A common question. Okay, right. Now let's say something like this. The first situation is something like this. So this is a proton, right? This is a proton. So what is the charge of the proton? Is it going to be positive or negative? Yes, it is going to be positive, right? So these are some simple things. So this is a proton, so therefore it is positively charged. And it is moving in this direction. And here in this section, we have a magnetic field, right? And the magnetic field direction, let's say it is going towards the plane like this, right? The magnetic field is going towards the towards the plane, right? It is going towards the plane like this. Now, the question is, they are asking you to predict the movement pattern of this proton. I'll give you three answers. For the first answer, there's no deviation of the proton, right? No deviation. So this is answer A. And the second answer, the proton moves in a direction like this. And the last part, the correct way will be, it will be moving in a straight line afterwards. So this is answer B. And the next answer, proton moves like this. Answer C. Right. So I'll give you a few more minutes, few seconds. Use your knowledge, which we discussed here in the previous case, and deduce the direction. Just give me the answer, whether it is going to be A, B, or C. Just use the chat box. And what is the rule that we are going to use? That is the yes. So how to predict or how to know which rule is going to be used here? It is going to be whether the Fleming's left-hand rule or the right-hand Searle rule. You need to judge it. So here we are dealing with what are the factors? We are dealing with the magnetic field direction. So that is the B, magnetic field. And they are asking what is the direction of the movement? What is the direction of the movement? right? So here, in this case, I said, if they ask about any sort of movement of an object, then definitely we are dealing with the Fleming's left-hand rule, right? We are dealing with the Fleming's left-hand rule. So we are using the Fleming's left-hand rule, right? By using Fleming's left-hand rule. By using Fleming's left-hand rule. Okay. So now you need to draw this diagram and you need to place your fingers. You need to rotate your hand according to that, okay? You need to rotate your hand. So Fleming's left-hand rule, here you get the force. In this direction, you get the magnetic field direction. And here from the middle finger, you get the current direction. So since this is a proton, current direction will be same as the direction of the movement, right? It will be same as the direction of the movement of the particle. So current in this direction, which means the middle finger, right, will be placed in that direction. Okay. So I'm explaining this question. While I'm explaining, you need to rotate your left hand and see, right? So there are no any methods, right? In order to deduce this answer, there are no any other methods. So definitely you need to use the left hand. You need to place your fingers according to like that in the perpendicular manner, and according to that you need to adjust, or which means like you need to rotate your hand, right? You need to rotate your hand and you need to guess the direction. So the current direction will be given in the middle finger. So you need to place it like this. And now the known factor is the magnetic field. So here crosses means the magnetic field is going towards the plane, right? Which means the index finger is pointing towards the table, right? It is going towards the plane. So magnetic field is in this direction, right? The magnetic field is in this direction. So therefore, what has happened eventually, the thumb is pointing in this direction. So which means the force being applied here. So this is the thumb, and B, it will be the index finger. So I'm not going to write it. Yeah, the answer is B. So which means eventually this particle will be experiencing an upward force like this until it is inside this magnetic field, right? So remember, until it is inside this magnetic field, it will be experiencing an upward force like this. So therefore, the path will be changed, right? It will be achieving this curved path. And from here onwards, there's no force. So therefore, from here onwards, it will be moving in a linear line. Okay, it will be moving in a straight line. But here, this section, it is because of the force applied using the Fleming's left-hand rule. Okay. Tell me whether you got it or not. Okay. So, right. Something like this. Okay. So I'll explain it once again. So the particle, the positive particle, right? A positive particle is moving in this direction. The positive particle is moving in this direction. So this is the direction of the current. This is the direction of the current. And in the meantime, what will happen is that the particle will be entering into a magnetic field, right? It will be entering into a magnetic field. So the magnetic field is towards the plane. ඒක අර plane එක ඇතුළට යන්නේ. So now use your thumb, use your left hand, right? So place your fingers accordingly as in the Fleming's left hand rule, right? Place your fingers accordingly like this. So if I draw the placement, no, I can't draw it actually, right? So mm, the direction of the current. So this is going to be the middle finger. This is going to be the middle finger. So in this direction, the middle finger will be placed. And in order to get the magnetic field direction, so the index finger, it is pointing towards the plane. It is pointing towards the plane. Then what will happen? The thumb is eventually placed in this direction, right? The thumb is eventually placed in this direction. So which means there's a force. So thumb gives us the force direction. So there's a small force being applied like this. So therefore, the particle will be moving in a curved path, right? So I'll give another question, something like this, right? Then try to apply the Fleming's left-hand rule and try to get the direction. So we'll say something like this. Question 2. So in this manner, I'll use the same particle, proton. Now it is entering into a magnetic field. Uh, it is entering into a magnetic field. The magnetic field, the direction of the magnetic field is pointing towards you, right? These dots, it represents not the holes, right? These are not holes. This means the the magnetic field is pointing towards you, right? Okay, so give me the answer whether the particle will be moving upwards, downwards, or whether it is going to have any sort of deviation or not. So path A, path B, and this is going to be the path C. Yes, place your fingers and see. Place your fingers and see. Otherwise, like there's no method of getting these answers, right? Path A means there's no deviation, which means there's no force, right? If you are not experiencing any sort of a force, then the particle won't be having any sort of a deviation. But if the particle to be deviated, then definitely there must be a force, right? Yeah, I'm getting answers, but right, I'll explain it once again. So this is a proton, and the direction of the positive ion, it gives us the direction of the current. So which means the current is now in this direction. So place your middle finger in this direction, right? So the middle finger like that, in that direction. And now, so the next given data point is the direction of the magnetic field. So here, these dots, it represents the magnetic field is coming towards you, right? It is coming towards. It is coming towards you. Yeah, I'm getting the correct answer, right? So which means the index finger must be rotated, your hand, right? Index finger must be pointing towards you, right? The index finger, while keeping the middle finger, in this direction, right? While keeping the middle finger in pointing in this direction, you need to rotate your hand, and the index finger must be pointing towards you, right? The index finger must be pointing towards you. Okay. So which means here I'll draw the diagram. Yeah. Mm. So now the magnetic field is in this direction, right? The magnetic field, it is coming towards you. Magnetic field is coming towards you, which means the index finger is pointing towards you. So eventually what has happened? Now the thumb is pointing downwards. So here this is going to be the thumb. Thumb means that is the force being applied. That is the force being applied. So which means once the particle entered to the magnetic field, right? Once the particle is entered to the magnetic field, there will be a small force acting downwards like this, making the path a curved one. So therefore, it will be following the path C. It will be following the path C, right? Okay, so yeah. will write down this thing. So I'll keep the board like this and make your own notes, right? Make your own notes. I will give you a few more minutes. Then I will give you another question to get an answer. Okay. If you are having any trouble, just ask me, just drop me a message, then I can help you. I can uh, explain that thing once again, right? So in these two situations, I have used the same particles. The same particle means the charge value, right? So here we are dealing with the positive charges. And now tell me if I ask you something like this. So instead of the proton, we are using a neutron, right? Instead of the proton, we are using a neutron. So now what will happen? Yes, use the chat box and tell me. Now we are using a neutron instead of the proton. Yes, I think you know the difference between protons, neutrons, and electrons, right? So that is directly in a relationship, having a relationship with the charges. So proton is a positively charged one, electron is a negatively charged one, but neutron, it does not have any sort of a charge value. So there's no charge means, is there going to be any sort of current generated? Yes, there won't be any sort of current generated, right? So that is the main thing of covalent bonds and all the stuff, right? We cannot conduct electricity through covalent bonding. The reason is you don't have any sort of like delocalized electrons or movable ions, right? So same thing applies here. If it is neutron, so the charge value is zero. So therefore, there won't be any force applied. So definitely, there won't be any sort of deviation. So actually, it doesn't care about the magnetic field. It just goes through the magnetic field. So according to these two questions, if it is a neutron, it will follow the path A, right? There won't be any sort of deviation uh, of its path, right? The reason is there's no electric effect, like there's no current generated. So no current generated means you can't use the Fleming's left-hand rule. So therefore, no force will be applied on the particle. So therefore, there won't be any sort of deviation, right? There won't be any deviation if it is a neutron. So I'll write down that also. So if it is a neutron having the charge 0, there won't be any deviation in the path. There won't be any deviation in the path. You need to think it, right? I'm not going to give you the answer. You need to think it. Why? What is the reason, right? So the answer is there's no current being generated. So no current means we cannot apply the Fleming's left-hand rule. So therefore, no Fleming's left-hand rule means the force effect won't be come in handy here, right? So therefore, there's no force being applied. Therefore, it won't be having any sort of a deviation. So therefore, it will follow the path A without any sort of deviation, right? Okay. So the next question, question 3. So this is important. The reason is it's never been tested here. There was only one question actually, and even in the textbook also you don't have this theory part. But here, since it was tested in a regional paper, I can't remember actually. So that's why I'm going to discuss it. Okay. So let's say something like this. So in this case, I am going to use an electron, and I'm going to project it in this direction. And here also I am having the magnetic field. So I will give the magnetic field to be going towards the plane, right? This is an uniform magnetic field. It is going towards the plane like this. So I am asking whether the path is going to be either A, whether the path is going to be B, or is the path going to be C, right? So here also we are using a particle, and remember the particle, the charge of the particle is negative, right? Charge of the particle is negative. Okay. Towards the plane means like just think it as a 3D space, right? So the drawings are done in a 2D space. So the surface that I have drawn these diagrams, it is a plane, right? It is just a plane. And if it is going, so something like this, just imagine, so this is the plane. So this is drawn in another dimension, right? So on this plane, I have drawn uh, different sort of things. And if something is going through that plane in this direction, we can say it like this. And if it is coming towards you, it will be like this. This is not the perfect example. So going through the plane, like going towards the plane, it is like going away from you, right? In these cases, where is it? This thing, right? If it is coming towards you and going away from you, uh, how can I explain it? It's hard. Like the reason is like we are using the 2D planes to explain this stuff. Like, so it is actually difficult to explain here, right? Just imagine something like this. I have placed a cardboard like this, right? So this is the cardboard sheet that I have used, or A4 sheet. So this process means this parameter is going through it like this, right? So the magnetic field is going through the board like this. And if it is coming towards you means it is coming towards you. So you are observing from here, right? You are observing from here. So if it is coming towards you, this means like this. And if it is going away from you, it means in this direction. So those are two different directions. So that is the simplest way I can explain it, right? And yeah, Lavidu, if you're having any trouble understanding that thing, just drop me a WhatsApp message later on, then I'll explain it further, right? Okay, so here we'll discuss how the direction occurs here. So this is a negative particle. So when it comes to a negative particle, that is an important thing, right? So here I have given, if there's a negative species, right? Sorry, if there's a negative species like electron or any sort of a negative species, the movement, if the movement is from right to left, then the current direction is opposite to it, right? If the movement is from right to left, the current is opposite to the movement direction. So here, the movement is from left to right here, right? The particle enters like this. So therefore, the current, right? So therefore, the current is going to be considered in this direction, right? The current going to be considered in this direction. So again, use the Fleming's left hand rule, right? Fleming's left hand rule. So current in this direction. So current in this direction means you need to place the middle finger in this direction, right? The magnetic field, it is going away from you, which means the index finger is pointing towards the table, right? It is pointing away from you, right? So magnetic field pointing away from you, that is the index finger. So eventually what will happen? The thumb will be in this direction, right? The thumb, yeah, the thumb is pointing downwards. So this is the force direction which you have the thumb here. So therefore, what will happen? There will be a small force applied downwards like this. So therefore, the path is going to be path C, right? The path is going to be C. So this is actually a special case, still not tested in your papers. As I mentioned, it was given in, as I can remember, it was given in regional papers or something like that. Okay. So remember, they will ask you to deduce the direction by using the Fleming's left hand rule. Okay. Yeah, so if you need anything to note down, then note it down. Then we need to discuss about the electric motor. So I'm going to switch into another screen here. Right. So this is the yeah, internals of an electric motor, right? This is the internals of an electric motor. So here you can, like, you can just separate the parts and you can actually observe these parts which are inside the motor. Okay, never mind. So here you have a permanent magnet placed like this, right? You have a permanent magnet placed like this, and the power supply will be like this. So we need to give the power supply, and there's a circuit going like this, and there's a pivot like this, and it is being attached. So clearly observe the diagram, right? Okay. So here you can see this split ring, right? Split ring. So that is being attached with a loop of wire like this, right? It is being attached with the loop of wire like this, right? So once you switch on the circuit, so there's a current being going like this, right? There's a current going through the circuit like this, and it reaches the carbon brushes. It reaches the carbon brushes. So afterwards, what will happen? That current will be moving. So I'll use a highlighter, then you can clearly observe the path. So the current will be moving in this direction, reaches the carbon brushes. So afterwards, it will reach this blue loop of wire, and this direction, it will, the current will be moving in this direction, right? It will be moving, and through the loop, it will be moved, and again returns to the split ring carbon brush and returns to the terminal negative, right? So that is the path of current. The main thing here is that, so as in the previous case, what will happen is that we have placed this wire or a loop of wire inside an uniform magnetic field. We have placed it in the uniform magnetic field. So here in this direction, you are having a current, and in the next situation, you are having a current in this direction. So now it is your chance, right? So apply the Fleming's left hand rule. I'll label these, yeah, I'll label this one, this path, this section is to be A, and this section to be B, right? The section of wire, right? This thing. This is A, part A, and this is part B, right? Now use Fleming's left-hand rule and see whether the direction of the arrows are correct or not. Yes? Is the movement, are the movements are correct or not? Right? Use the Fleming's left-hand rule. Yeah, good. They are correct, right? So, which means, so here you will be getting some sort of a rotation. So in this way, and this part will be moving in this direction. So that loop is actually connected to this, what do you call this? Yeah, pivot, or we can say this rod. So eventually it will be rotated, right? It will be rotated. So that's how the motor works, right? So and remember this this sort of a diagram was also given in a question paper. I'll if we have time, we'll show it, right? I will show it. So this is the working mechanism of the electric motor. So just imagine I'm going to change the direction of the terminal, right? So in this case, I'll draw here. I'm going to I'm going to, yeah, I'm going to use the terminal in this direction, right? So this is going to be positive and this is going to be negative. So which means now the current moves in this direction and returns in this direction. So what will happen? Now what will happen is that now the rotation direction will be in the opposite way, right? So instead of this clockwise direction, now you will experience a rotation in this direction, right? You can apply the Fleming's left-hand rule and you can see for yourself, right? So apply the Fleming's left-hand rule and see. Okay, so this is the theory behind the motors, right? So I think all the necessary theory points are given in your workbook, so I'm not going to ask you to draw this. So please read and try to get the understanding, okay? So these are DC current motors. So DC means you are having only one direction current, right? So which means this will be rotated non-stoply, okay? Right. Then to increase the rate which the motor turns, so we can increase the number of loops, right? And we can increase the strength of the magnetic field, and even we can increase the current in the loop of wire. So these are some common things you need to remember. You have to remember them, okay? So there will be like direct questions asking how we can increase the speed of the rotation of in the motor. Then these are the three factors that you need to write, okay? Right. Then yeah. Then the electromagnetic induction part, okay? Electromagnetic induction part. So here you can see that actually we discussed this thing, right? We discussed this thing. So once right. So wire is being placed in an uniform magnetic field. So so in this case, we are not providing any sort of an external power supply. So here the very first thing that we discussed, instead of this ammeter, we had the power supply, right? We had the power supply like this. But in this case, what has happened? There's no power supply. Instead of this power supply, we are using an ammeter. So what is the main purpose of the ammeter? The main purpose is in order to get an idea or to get an get a value of the current which is flowing through the system, right? So which means we are thinking that because of the movement of a wire inside the magnetic field, it will generate some sort of a current. So in the previous case, uh, so we thought that if there's a moving current, then there will be a magnetic field generated. Then there will be a magnetic field generated. So this is the first thing that we discussed today. Now we are telling that, right? If there's a magnetic field and we are moving a wire, if we are moving a conductive material, then a current will be generated, right? So here magnetic field is being generated, but in this case, a current will be generated. So that is the thing that we are discussing here. So that is known as the electromagnetic induction, right? Electromagnetic induction. So the current that is going to be generated here, we can increase it by moving the wire more quickly, having a higher speed. So the main thing is that we need to cut these magnetic field lines, right? We cannot have these continuous magnetic fields. We need to cut these magnetic field lines, which means we need to move the wire more quickly, right? And by using a strong magnet, so which means we are using a stronger magnetic field. And instead of using this single wire, then we can use a wire which is something like a wrapped one or a coil like something. Okay. So this is the theory behind it. That is something like what you call moving a magnet and generating electricity. So something like this, right? So here the wire is placed like this and the magnet is being used. A magnet is being moved through the coil, right? It is being moved through the coil. So eventually it will generate a current. So that current can be, uh, the value can be gained using the ammeter, right? So that's why it is mentioned as the induced current, right? That's why it is mentioned as the induced current. So how can we get the direction of the current here? So now here also we are using the right hand swirl rule. Okay, we are using the right hand swirl rule. So this is going to be the direction of the magnetic field. So your thumb is going to be placed in this direction. So thumb in this direction means all the other four fingers will be bent like this. Ne? You can do it by yourself and see, right? Which means current will be generated in this direction. So the current will be having this direction, right? So that is a hint actually, right? So remember the right hand swirl rule, it can be used in two different directions. So the first one is you can place the thumb in this direction where you have the current. And because of that, the other four fingers will be bent like this, which gives the direction of the magnetic field. So that is one way of using the right hand swirl rule. And the other way is that you can place the thumb and you can use it as the magnetic field, and the generated current direction, it will be given by the other four fingers, right? So remember, right hand swirl rule can be used in both situations, right? In both ways. Okay. So here also we are using the right hand swirl rule in order to get the direction of the current. And here also some factors are being mentioned to use the what do you call that, to move the magnet more quickly, to use a stronger magnet likewise. And Yeah, we need to discuss about the generators and the transformers. Ah, yeah, we can finish the lesson today. Right. So when it comes to generators, so that electromagnetic induction theory is being used there, right? So as you can see here, the smallest generator that we can find, not today, actually, not in day-to-day life. You might have seen this equipment, I don't know, right? So this is called a dynamo, and this is something like a small bottle actually, right? Which is made out of steel. But there's a huge working mechanism inside that. So this thing is actually like here you are having a spinning wheel actually, and it is kept in touch with the tire, right? So once the tire is moving forward, which means rotating in this direction. So this wheel is actually touching the surface. So therefore, this wheel will be also rotated, right? This will be also rotated in this direction. Okay. So there's a rod connected to the wheel here, and that rod is connected to a magnet. So eventually, when the tire rotates, the upper part of the dynamo will also rotate. So therefore, what will happen? This magnet will be also rotating in this axis. Okay. So surrounding the magnet, right? This is a circular structure, and surrounding the magnet, there's a soft iron core, and a coil is being wrapped around the soft iron core, and it is being directed towards the battery, or in some cases, it is being directed directly to a bulb like this, right? So you might have seen this thing. Once the bicycle is moving, that is the only place where the bulb will switch on, right? So otherwise, like you might have seen this thing, right? So once the speed reduces, the luminosity or the intensity of the or the brightness, right? The brightness of the bulb decreases. And if you are moving in a higher speed, what will happen? The brightness increases, right? The theory is that thing. So when you are moving in high speed, what will happen? The magnet will rotate in a higher speed, right? So therefore, a huge amount of uh, electricity will be generated in this coil. So that will be directed towards the bulb, and the brightness will increase. But in the meantime, what will happen if the speed is decreasing, what will happen? The rotating speed is lower. So therefore, a small current will be generated there. A small current will be generated there. So this is the main theory behind the dynamo. Okay. So if there's a question given in the exam, so you should be able to explain the theory here, right? So remember, there's a rotating magnet inside the what do you call this dynamo. So the same theory is being applied in turbines as well, right? So normally turbine, you are having that spinning wheels actually, right? So when the spinning wheel rotates, there's a magnet being rotated. So when the magnet is being rotated, what will happen? There will be a current generated. So the magnetic field lines are being cut. So therefore, there's a current being generated. So that current will be directed towards the grid and for further users. And when it comes to the transformer, so transformer is something that we use uh, to change the what do you call the voltage, right? So I'll use a different shared screen. Then yeah, right. So in a transformer, so we can change the voltage given into a desired voltage value. So in order to do that, we are using the transformer. So that is the main idea of a transformer, right? So here in a transformer, we have a soft iron core like this. And so we'll take the alternative current. Okay. So this is my alternative supply, and it is being attached to wires. And this section is wrapped like this. Okay. Then like this. And there's another coil where you have a different number of wrapping, and it is also connected to a supply. So this is actually the V out, and this is the V in, the input values, right? So the input section, that is known as the primary coil, right? Primary coil is the section where you have the input voltage, and the other one, that is the secondary coil, where you have the output voltage. Okay, so this can be in opposite directions. Opposite direction means, so in this diagram you can see the primary coil is having more number of turns with compared to secondary coil, right? So it can be changed actually, right? Okay, so here uh, the theory that you need to remember is that the voltage is directly proportional to the number of turns in the coil. The number of turns in a coil, right? So we can write it as V directly proportional to the number of turns. Number of turns. So by using this theory, we can get an equation. So the first equation that you need to remember when it comes to transformers is this thing. Input voltage over output voltage will be equal to number of turns in primary coil over number of turns in secondary coil, right? So if you are using the symbols, you can write V in over V out will be equal to NP over NS. NP is the number of turns in the primary coil, and NS is the number of turns in the secondary coil. Okay. And the next point that you need to remember is that when it comes to transformers, there are two types of them. The first one is step down transformers, and the second one is the step up transformers. This is actually easy to remember. So step up means you are getting a higher V out from a low V in, a higher output voltage from a lower input voltage. So in order to get that, the number of turns in secondary coil must be higher than the number of turns in the primary coil, right? So in order to get the V out value, a higher value, you need to have more turns there, right? And the, oh, wait, the other way around, okay? So I made a mistake here. Step down means you are having a low V out value. And here it is V in, right? A higher input voltage. So therefore, N primary is going to be higher than N secondary, right? This is the idea of step down. Stepping down, you are reducing the output voltage. You can remember it like that. You are reducing the output voltage, okay? And for the step up, you are increasing the V out value. You are increasing the V out value. So therefore, N primary is lower than Ns, right? N primary is lower than Ns. The number of turns is lower than the secondary coil, okay? Step up and step down. So remember those points. And according to this diagram, this thing is drawn as a step down transformer. The reason you can clearly see there's a less number of turns in the secondary coil. Okay. Then the next equation that you need to remember is the power equation when it comes to a transformer, right? So that is the power equation. So in order to get the power equation, there's an assumption. So the assumption is that uh, these transformers are ideal transformers, which means there's no wastage of power. They are 100% efficient. They are 100% efficient. Okay. So here we can write, we know that the power equals voltage into current. Power equals voltage into current, which means P equals VI. P equals VI. So if the transformer is to be 100% efficient, then the P in must be equal to output power. So which means we can write voltage in multiplied by current of the input must be equal to voltage output into current of the output, right? So the IO. So this is the power equation. So we have two different equations. This is the first one with the number of coils to get the number of the value of the voltages. And the second one, if we are dealing with current values, then we can get this. And instead of writing V in and V out, we can write something like this. V primary into I primary will be equal to Vs into Is. Same equation in different manner. Okay. Just two equations. The first one is V in, or you can write it as, this thing also can be written as V primary over V secondary equals N primary over N secondary. I think it is easy to remember, right? Vp over Vs will be equal to Np over Ns. And here the other one, Vp into Ip is equal to Vs into Is, right? Yeah, there are some calculations here. You need to go through them, and next week also we will be discussing about the calculations. And there's another part that I need to discuss. So I will discuss about the national grid next week, right? I will discuss about the national grid next week. And yeah, so these are the things that I want to discuss today. So remember, I will be giving you homework. So you had your vacation. So print out those magnetic field, take the hard copies of that magnetism question tools. And if you don't have it with you, I can upload it to the WhatsApp group. So please engage in those questions. So definitely seems we have covered like 98% of the lesson. So next week it will be just question discussion session. Okay, question discussion session. So I don't want you guys to be like, just looking at the screen. I want you to first, you need to engage in these questions and get an idea. You need to have those difficult points, right? Otherwise, no point of me doing these all these questions, right? I have done all the exams and I have passed them. So there's no point of me conducting all these calculations. So you are the ones who need to do the calculations, right? So please take the hard copies and within this week, try to complete them. And so, as I mentioned, next week will be discussion session related to magnetism from the very first part, right? Which means the whole tute will be discussed within, let's say, within the next day or so. And there's a small part that I need to discuss about the national grid. So please go through them and have an idea about it. Okay. Right. So I'm going to conclude the session for today and try to complete those homeworks by next week. Okay. And if you don't have the question tube with you, just drop me a message. Then I will re-upload that again. Okay. I'll upload that again. Okay. So thank you for joining and have a nice evening. Okay. Okay. Bye. And as I mentioned, if you're having any trouble, just drop me a WhatsApp message. Okay. Right.